As David said, I'm going to tell you a little bit about space-based solar power, why that is so much of interest at the moment, and of course the company that I'm chair of, Space Solar, and what it is that we're actually trying to do. So I'll let this slide build so you can see some of the challenges that the energy system faces at the moment, but fundamentally. So the energy system, the global energy system, is currently in the grip of three different but related crises, which together are contributing to the climate crisis that we all face. And those three energy crises are, firstly, and the one that we're all very familiar with, is that the way that we've been powering our economies for the last 200 years is choking our planet. And we fundamentally need to change the way that we generate power and that we use power in order to maintain the viability of life on Earth as we know it. But that is only one of the three challenges we have at the moment, and it's one that sort of predominantly affects Western economies. The other challenge is that the demand for energy is currently growing at an unprecedented rate. And even in the time that we've been operating as Space Solar over the last couple of years, expectations for needs of energy over the next 15 or 20 years have doubled, and they're continuing to grow. Currently, we estimate that demand for energy in 2050 is going to be about 4 times what we currently produce at the global level. But there are estimates that go much higher than that. You'll have heard Eric Schmidt, possibly in his recent evidence to Congress. He said that the current US energy supply is going to be used by 99% of that is going to be required purely for AI. Didn't give a time frame on it, but he was clearly very bullish in his expectations of demand for energy growth in the US, purely driven by artificial intelligence. And the third energy crisis, which I think the one that many people forget about, and that's the energy crisis in the developing world. So there is huge demand, unmet demand, even now for energy, sustainable or resilient energy in the developing world, which is holding economies back. And we know that if left to their own devices, in the absence of other solutions, as we're already seeing from the likes of India and China, then these countries are going to build out new generations of energy systems based on carbon fuels, on gas and coal, or whatever is the most cheap and easy to use for them. So that this is another energy crisis that's going to be contributing to the climate crisis in the years ahead. And when we look at the problems we have here in the UK, or our energy policy here in the UK, we're only really looking at the first of those three sets of problems. And maybe a little bit at the second. We've got some growth in energy demand built into our plans, but fundamentally we're looking at the transition of our existing power and the decarbonisation of our existing power system. And even then, if you look at the economics of it, here we have we've actually put together all the costs that are in the existing plans to achieve decarbonisation of our grid by 2030. Top them all up at the bottom, and you end up with a total cost of £240 billion needs to be spent to achieve this between now and 2030. That is 5 times even the current estimate of the costs of HS2. And there is very little sign that this amount of capital is being mobilised, or anything close to this amount of capital is being mobilised in order to meet these problems. And so, and that's just to solve one of those three problems. So at the moment, globally, our solutions to climate change are not tenable. Just as an example, here we are in the UK, Boxing Day 2024. So in the winter, the short cloudy days, it's quite common for the solar power to contribute less than 1% of the energy demand that we have in the UK at the moment, despite the investment that's been made into it. And when the wind stops blowing as well, and that can get down as low as 6%, which means that we're still reliant on 46% from gas, 20% coming in from imports. So when we're looking at decarbonising, we're looking at national resilience, being self-sufficient in fuels, in energy, we're a very long way from that. And even the plans that we've got in place now, you have to question whether they're actually going to get us there. So we need new solutions. There's no question about that. So this is where space-based solar power comes in. So I'll talk about what it is we're actually proposing, but fundamentally, what we're looking at space-based solar power. If you have a solar power plant in geostationary orbit, then you have 24/7 baseload and dispatchable power. What that means, it's there all the time. It's reliable. It will provide you your background energy solution. It's not dependent on local weather conditions. And what the dispatchable element means is that, as you can see from the sort of the image we have on the screen here, and a satellite in geostationary orbit, that will be able to see about a third of the Earth's surface. So it can distribute power to anywhere on that area of the Earth that it can see and change and move where the energy distribution goes at a flick of a switch. I mean, that's completely changes the dynamics of mobility of energy. And so I think this is a completely new concept for what a global energy system could look like. It's also got the potential to be the lowest cost of energy at £24 per megawatt hour. It's scalable, so if you want more power, you put up more power stations in orbit, and and there's plenty of space up in orbit, in geostationary orbit. I should actually say they don't need to be in the same ring of space as the communication satellites are at the moment. They can be in inclined orbit or with slightly eccentric orbits, so they can keep well away from the communication satellites because they don't have the requirement for precise pointing accuracy from the ground that the communication satellites have. Sustainable, low carbon footprint. It's flexible. It's exportable. It's very high value. I think just imagine having an energy system that you can distribute power to on demand anywhere on the Earth. And fundamentally, particularly compared with fusion, it's the physics are well understood. What we're solving now are engineering problems, and we have a development plan which could bring the minimum viable product, the first commercial solutions, into service within 5 years. So, so lowest cost of energy, it's good as £24 per megawatt hour, very compatible with existing intermittent renewables once the capex has been expended. And the capex itself is about a quarter of the cost of nuclear. So what does a space-based solar power station look like? So if we look at the diagram on the right here, so where we can see the number 1, we can see sunlight coming in from the sun. So these reflectors at the top and the bottom of the power station, we have this helical structure in the middle, which I'll say a little bit more about in a moment. So these reflectors at the top and the bottom are always oriented towards the sun. So these put on towards the sun, these are receiving the incident sunlight, and they are reflecting sun down onto this helical structure. And this helical structure you should think of as a sort of a spiral staircase. So around that helix, you have a number of staircases mounted, and there is a picture later on where I can show you what these things look like. And that's where your solar cells are. And it's also, every solar cell is attached to a transmitter. So across the whole structure, we have solar cells and transmitters, so that the whole structure operates as a giant phased array. And then, so each one of those transmitters is taking energy from the solar cell and broadcasting it in the same frequency towards the Earth. And you use the principle of a phased array in order to steer the beam. And so you can, by changing the phase of the transmitters on the actual structure, you can steer the beam around, and that is how you manage how the beam is transmitted to different points on the Earth. And this is one of the big advantages that we have currently over other designs for space-based solar power, is that we have no moving parts on board the spacecraft, which others have in order to steer the transmission beam. And that means that we have, it's much lower cost, lower weight, because the movable parts are necessarily heavy to actually have a gimbal joint that's capable of taking gigawatts of power across it. And also it means that we're much lower maintenance, much longer lifetime in orbit, and I think that's what gives us, our solution, the competitive advantage just at the moment. And you'll see this is for the Merlin solution, the geostationary solution. So this will give us a power of about up to 2 gigawatts. And this is the sort of structure that we'd be looking at putting into geostationary orbit, which is up to 1.4 kilometers across. And what does the receiving stations look like on Earth? So the actual infrastructure on the ground is very straightforward because you're transmitting a low energy density beam of monochromatic microwaves. So it's all very tailored to the one frequency. So you basically produce a net of dipoles, and which you can either locate alongside other pieces of infrastructure. So you could put it over the ocean, co-located it with an existing wind farm, or if you're using it on ground, you can put it on poles, as we see in the diagram there, and you can use the land underneath for for agriculture or for whatever else you might want to use it for. And in terms of use of space, then you get about from a 3.5 square kilometer diameter receiving station, you get 0.6 gigawatts of power, which is 8% of the area you would require from an offshore wind farm to get the same amount of capacity of power generation, or 40% of the area versus a solar farm at peak power production. So and of course you get that dual use of the land when you're putting it on the ground. So the economics of space-based solar power are driven by this concept of a specific power, and so this is the amount of power you can generate per unit mass in space, because actually getting the mass into space is purely what drives the economics, the number of launches you need in order to get your structure into space. And you can see there, these are the two leading other designs around at the moment for really large-scale energy production. There's one from China and one from the US, and ours is 8 times more efficient than the China's solution, and sort of 2 and a bit more than the current USA best model. And I think that's what makes ours just cross the threshold of economic viability. While I think they've still got more work to do to make that possible. An example of some of the orbits that we've been looking about. I've been talking about the geostationary orbit, which is where our largest power units are going to be. But there are other orbits that are potentially valuable that we've been looking at. An 8-hour highly elliptical orbit has pretty good levelized cost of power, so levelized cost of electricity, the LCOE. It's not quite as good in terms of having the availability, so it's about 75% available for any one place on Earth. But so if you're combining that with other renewables, that can close a business case in some circumstances. And even the polar low Earth orbit, which is the worst in terms of the actual cost per unit of power, there are use cases, particularly at the poles. We've been doing a lot of work with the Antarctic Survey. They're very interested in being a launch customer for us. Even at that high rate of power, given the logistical challenges of getting petrol and getting gasoline and fossil fuel power into the poles, and that actually becomes economically viable. So why is space-based solar power now viable? So ultimately, it comes down to the cost of launch. So the idea of space-based solar power, as David said, has been around for many years. The first record that we've found has been from Isaac Asimov back in the 1950s. But the barrier has always been the cost of getting the structure into orbit that's going to be generating the power. And the engineering abilities to actually do the manufacturing. Now, all of those things are coming down now, and so now with the likes of Starship coming from SpaceX and other very heavy lift vehicles that are coming to the market at the moment, all of these things are becoming possible. And if you see the prices that we've got down on there on the right hand side, in my lifetime, price has gone down from a factor of 10, from about $20,000 per kilogram down to about $2,000 per kilogram. And that's expected to come down even further over the next 15 years. And our model is very conservative on where that's going to get to during our early launches. So we're only assuming somewhere between $1,400 and $1,000 per kilogram for our calculations. So I'm talking about the cost of energy and compared with other renewables that we're going to be producing with space-based solar power, which is 24 pounds per megawatt hour earlier. So if you put in the 10% hurdle rate there, that's going to make it commercially financeable, you end up with 26. You compare that with the intermittent technologies. When you're being optimistic, you come up with figures like 33 megawatt hours, 41, 44 for offshore and onshore wind. The combined cycle gas turbines combined with carbon capture, that gets you somewhere about 82. Pressurized water reactors, the new nuclear systems coming online, they get you to about 96, and biomass is at 98. So when you're looking at the base load technologies we get down at the bottom, we're much more cost effective than those. And if you try and make the intermittent technologies potential baseload technologies by putting in storage and other technologies, then you're ending up with prices like that. So how would space-based solar power be brought into the energy mix of the energy system? So this was a piece of work done by Goran Strabach of the Department of Electrical and Electronic Engineering at Imperial College. He did a fantastic piece of work for us as one of the studies we did early on, looking at how would we integrate space-based solar power into the UK energy system. And as you see, as we depending on how much you build in, so looking at 2 gigawatts up to 8 gigawatts, then the more you include, the lower the energy system, the cost of the energy system becomes. And so if you are able to bring in 8 gigawatts of space-based solar power into the UK energy mix, then the cost of the whole energy system comes down by about £4 billion per annum. And interestingly, it's not predominantly the nuclear energy that it displaces as another baseload energy source. We suspected that might be. It's actually the renewable energy that it displaces. So it reduces our amount, the need to build out the renewable energy systems that we have at the moment. So we don't need so many offshore wind farms and solar panels in fields and what have you. Looking at comparing some of the other aspects of comparable renewable energies, the three things that we focus on are energy security, the environmental impact, and the global impact. Generally, most national energy policies focus on the first two and miss the third one. I think that's where actually space solar has a unique advantage, and recognizing that we need to solve this problem globally, it's something that we do need to focus on. I think if you look at, and I won't go through all of these things in detail, but on energy security and environmental impact, if you look at a mix of these technologies on the left, you can sort of build a pathway through to convince yourself you've got an effective solution. But when you're looking at the global impact, all of these other competing technologies have problems being able to either the technology is not mature enough, or they're not globally scalable, or they're difficult to export. And I think this is where space-based solar power would give us something really different to change the game at the global level, not just the national level. So some of you, just to try to preempt some questions what some of you might have around the efficiency of space-based solar power versus terrestrial solar. And again, I won't go through this in great detail, but here is the Sankey diagram of how efficient space-based solar power is compared to terrestrial solar. I think on one of the early slides it says it's up to 13 or 14% more efficient, and here you can see why. So the solar, you lose the big chunk of it out in space when you are converting the incoming radiation into the direct current to the transmitter, but then the transmission is all relatively efficient. It's quite efficient, and because you're using these dipoles and a tightly focused beam, your beam capture is quite efficient, and then you have a little bit more inefficiency in terms of when you're converting that back to AC at the bottom end. But with terrestrial solar, you use about half the incident radiation just because half of the time you're at night, so you can't use it. You also lose another big chunk at the ground, because your most inefficient part of the system is actually the conversion of the incoming solar radiation to DC current. So that's, you end up with this, roughly 18% efficiency of space-based solar power compared to the incident sunlight at the space station or at the power station, compared to between about 0.2 and 5%, depending on weather conditions on the ground. And looking at Saudi Arabia, so Saudi Arabia, or in the desert generally, we picked a picture of Saudi Arabia there, but the desert is often considered the optimum environment for solar power. And again, when you're looking at the economics of how you do that for a 2 gigawatt baseload system, these systems are being built and financed at the moment in some Middle East areas. So in order to generate 2 gigawatts for us to normal conventional solar power, you will need 53 square kilometers of rect tenor. For space-based solar power, you'll need 38 squared, so that's a better efficient use of land. You can use it for other things, which is much harder to do with terrestrial solar. You don't have the cost of all the battery storage and that you need in order to make solar power a baseload energy supply. All of which leads to a much more efficient carbon footprint and a much faster payback period for your, for your investment in energy infrastructure. And the other thing worth bearing in mind is actually there's a lot of evidence to say that putting solar panels in desert environment is actually having a very harmful effect on climate change, because you're losing the albedo component of the sunlight reflection that you generally get in desert environments. If you're putting big dark surfaces over the desert, then okay, you're getting quite a low efficiency of transmission into power. All the rest of that incident radiation is getting converted into heat and is just radiating back into the atmosphere. So you're losing quite a lot of, or having a secondary impact on climate change. So this is the space solar team. The space solar is genuinely leading the way in space-based solar power. It's one of the things that some of you know. I used to be the CEO of the Satellite Applications Catapult before I took on this role, and I think it's one of the things I'm proudest about of our time at the Catapult is that we really reawakened interest globally in space-based solar power. And I think that that extra that couple of years we had at the start when no one else was really looking at it seriously, I think was a fantastic advantage for us. And I think now we do have a design and a concept which gives us a real opportunity for doing something groundbreaking in the UK that nobody else is yet in a position to do. So obviously it's a time-limited opportunity, but we are there. And these are some of the things that we've been doing most recently to advance the engineering capability and demonstrate the concepts of how we actually do this. So the Harrier 360-degree wireless beaming demo. So this is a very small structure. It's about 2 feet across. To give you some sense of scale, but it shows it's using those. You can see how on the left-hand side here, you can see how that staircase on the helical structure works, which you can see over here in the Harrier demo. And so we were just showing how using that structure to beam power, and you could rotate that structure and still maintain a constant power beam towards a receiver at the other side of that. That test environment, and that was demonstrated extremely well, and that's demonstrated the concept of power beaming. A lot of people are interested with that, and this is at the bottom we have our Albatross robotic truss builder. This is a project that we did together with the UK AEA folks down at Culham, their robotics centre down there, and it's a concept development for how we could extrude. Send up the raw material for our basic chassis, the structure for the space-based power system, and how we could extrude our own trusses and then assemble them as we go using this robotic system. And so that's a concept that we've demonstrated at a relatively low level to start at the moment, but we're pretty confident that that's going to be an engineering solution now that works out. A few that we've looked at. And here on the steps here for the actual, so what you're actually seeing is we have lenses at the edge of every step. I can't keep calling them steps. And we have lenses which focuses the light that's being reflected down from the reflectors at the top of the structure. And here we have concentrated photovoltaics, which are taking the highly concentrated solar light and that's coming through, and that's what enables us to generate much more efficiency than you can generate from photovoltaics on the Earth. The higher intensity of light that you have, the more efficient your ability to turn that light into energy. So, this is part of a completely new economy that's being generated in space right now. We're looking at a whole new set of concepts, and the idea that things that we're doing for these robotic construction, these are going to enable a whole new generation of uses of space. We're going to be able to make new space telescopes, do new ways of doing planetary science. We're going to have new factories in space. So I think that this is, I was saying to someone the other day, for most of my career in space, there has been comms, navigation, Earth observation, and space science, and that's kind of been it. But I think what we're now seeing, because of the economics of that we're seeing emerging from space, the new launch capability, the ability to build large structures in space, is that a whole new economic model for exploiting space and taking advantage of space is starting to emerge, and we're very much a part of that. Space Energy Initiative, just say something very briefly about that. So this is a partnership of companies all interested in being part of space-based solar power, being part of the supply chain. We've got many energy companies in there who are interested in being actually users of space-based solar power. We've got government partners in there, of course, who are absolutely vital at this stage, just to make sure that we're getting in line with all the regulatory and requirements in that regard. So that's kind of it, really. Just to summarize, the transition to net zero is urgent and important. So long as it's sustainable and affordable. I think we've got to look after our economy as well. I think space-based solar power is definitely going to contribute to that. But so is making sure that we increase capacity to meet future demand and maintain international competitiveness. If we don't have energy capacity in the UK that other countries do, then we're going to miss out, because there's going to be things that we can't be part of. And also energy equity for the developing world with access to abundant, clean, reliable and affordable energy. If we don't find solutions that are going to help the developing world make that transition too, then they're going to continue to build out their systems using fossil fuels. So, I'll jump straight to the bottom line here. The best way to predict the future is to create it. So, thank you very much.
Thank you very much, Stuart. A bravado performance. I think I've actually learned really a lot from what you've had to say, and the whole thing looks a little less like science fiction and a little more like something I might even see in my lifetime. You talked about your lifetime. Mine's pretty shorter than yours. Anyhow, so we're getting questions and so on, but I'll shoot from the hip first. Going back to science fiction, I remember back in the 20th century, we were always concerned about death rays and things like that. Now, here you're sending large amounts of energy from a space station down onto a fixed point on the Earth. What happens? Is that dangerous to mankind, or?
So, there are regulations about how much power density you are allowed to broadcast in the Earth. There are some aviation regulations which are there for people who produce radars and what power they're allowed to be in close to radar. But there are also terrestrial requirements around energy density as well for health and safety. So we're complying with all of those. And that's the reason why you need a larger area to collect the power. So you need to put the grid over quite a large area in order to keep the energy density down to levels which are compliant with regulations. So hopefully I can reassure you on that point. We're well within what the sun distributes to us all the time. So long as we can survive sunlight, there's no reason to worry about the transmission of power from space-based solar power.
Well, that is very reassuring. In fact, we had a specific question from Vince Harris about, is there a risk, e.g. to aircraft, being caught in the energy beam? What you're saying is they already run that risk with people using radars. As long as you meet the regulatory environment, you're saying it's
absolutely. We're well within the limits that radars already meet, so or are already required to comply with. So there's no reason to be concerned about that.
Is there any radiative interaction with the atmosphere? You lose some of your energy coming down.
Not much, actually. I mean, if we're looking at the sort of 1 to 10 gigahertz frequency range, which is actually pretty efficient at being propagated through the atmosphere. I think it's on the it's on that chart of where all the losses are in the end-to-end system. I think for the energy transmission, it's about 84% efficient. So we lose about 16% of the energy in the transmission, or something of that order.
But that turns into heat on the way down, or is it reflected, the bit you lose?
That's a good question. I think a lot of it will be reflected. Some of it will bounce off the top level of the atmosphere.
Yeah. Well, there's always, it's the concern would be if it's absorbed before it gets to you, because that could be changing the chemistry of the atmosphere. Okay. So I've had my cut of the first questions, but I think we've got a great list here. Bill, would you like to act as moderator for the
yeah, of course,
questions we've had in? Okay.
So if people want to ask the questions in person, please turn your video on and ask your question. Otherwise, I'll just ask them as we go through. So we've got two from Mike. So I'll take both of those really together. Yeah, about the lifetime of the solar cells in space and around solar radiation impacts. And that's something we're aware of. Sort of space vehicles in general have to have a degree of radiation hardening. And sort of a little bit related to that is around the maintenance. I think that question came up before you had on your chart about the maintainability aspects. Do you want to cover those two maybe?
Yeah, so we're expecting each certainly the large ones to be viable for at least 30 years. I think there will be some degradation on the solar panels. I think one of the design reasons for orienting the solar panels as they are, if they're sort of perpendicular to the direction of incoming sunlight, so they never face the sun directly. So what we're looking to do with the reflectors is just put the materials on the reflectors that just reflect the bits of the sunlight that we want to capture and let pass through all the gamma radiation, all the damaging radiation that degrades solar panels. So there's a bit of work to do on those materials, but I think we are expecting to get longer lifetime from our solar panels than generally what you achieve in orbit because of that. So we're working on a 30-year lifetime.
Okay, Mike, any follow up to that? Thank you for joining us.
Yeah, thanks, Joe. That was great. Really, I guess I was more worried about things like, solar flares and Carrington events, that sort of thing, where you might have a really bad radiation environment. Could that degrade things quickly?
It could do. I mean, you're going to be because you're not facing as I said, that you're not facing directly the sun, the actual cells. You're not going to get that direct incident radiation, but you will be, as that radiation impacts the environment around you, and you get all the other impacts from that. So there will be some impact from that. But
okay. So I guess my related question is how do you envisage maintenance? Because out in geostationary orbit, that's quite difficult, isn't it? So is that robotic maintenance or automatic systems which reconfigure bad cells?
Yeah, I mean, we are talking with the likes of Astroscale and people around, the both maintenance and also the the disassembly and potentially reuse of components and all those sorts of things, which are part of this new ecosystem in space. I wouldn't say we have all the answers for that yet at the moment, but yeah, I think at the moment we're certainly for the things that we're looking to build, the examples we're looking to build over the next 5-10 years, they would probably be models that we would put up there. We would expect them to last for 30 years, and then we would move them out of the way once and consider ways to retire them at a future date.
Okay, thank you.
Yeah, thanks. We got a question from Dave Gordon. I don't know, Dave, if you wanted to ask it, but it was around geothermal in relation. With geothermal's got some of the same characteristics of base load and on demand. So is geothermal in any of your comparative analysis?
I think geothermal is in that comparative analysis. I can bring that up now if you want to see it. I think shall I put that up now?
Yeah, if you've
Yeah,
got it to hand.
I'll bring that back up. So we have geothermal here. I think when you're looking at the national level and the environmental level, I think our assessment is that geothermal scores very well, but it's quite difficult to export geothermal power, and it's quite difficult to scale up geothermal power at the levels that we need particularly in the developing world. But yeah, I think at the national level we think there's a lot going for it.
Mm-hmm. Okay, great. Thank you for that.
Put that down. Yeah.
Just going down, yeah, Rob Williams about do you need any kind of control on board fuel thrusters to keep the array stable and pointing in the right direction?
Definitely.
Mm-hmm.
Yeah. There's a big piece of work going on in terms of how we do station keeping, how we do attitude control and all those sorts of things. Bearing in mind that we've got two great big solar sails at the top and bottom of the structure, that's going to be impacting orbital dynamics and attitude dynamics. So yeah.
Okay. Can I ask a sort of related to that? As you mentioned using a phased array approach rather than mechanical steering. So why did China and US not go for a phased array approach, since that kind of steering mechanism is pretty well proven in radar?
Well, their designs. They never thought to. They haven't thought to actually integrate the transmitter and the solar power system into the same single structure. They've gone to more traditional. Let's call it satellite architectures, where the transmission system and the power system are separated, and it's being able to do that and through that in particular through that helical structure, which gives you that sort of 360-degree continuous steering ability that enables you to do that. We've got a patent on that, and there's no other obvious ways of doing it. So that's where we get our competitive advantage.
Okay, that's interesting. Okay, how did the Patents Office kind of cope with that particular application? That must have been a tricky one for them to assess.
Well, I think they're used to some quite out there applications at the Patents Office.
Okay, thank you. So Asma, you've asked a question. Great, excellent step forward. Are there any drawbacks or issues? So apart from the ones you've hinted about, some of the engineering challenges, what are the primary challenges then?
So I think primary challenge is the financing it, the fact that you need this sort of upfront capital to build it before you can really demonstrate it. So that's the thing that's exercising us on a day-to-day basis at the moment. So we're looking to raise that funding right now. I think the recognition that this third energy challenge that I've attempted to highlight is actually what's going to derail all the activities to do things at the national level. And I think, even if, I mean, I'd love nuclear fusion to work. And I know that we're putting a lot of time and effort and money into nuclear fusion. When I did my degree in the sort of late 1980s, it was 30 years away then. And sort of guess what? It sort of, my feeling is it still is. But even if we have a breakthrough tomorrow, and in 10 years' time, we're able to have an operating nuclear fusion reactor, and it's at an acceptable cost. What's that going to mean on the international scale? I think so. My sense is that if we all of a sudden have cheap and abundant power from nuclear fusion, and that gives us a competitive advantage internationally because we have that cheap power, access to power, then that's actually going to drive more demand for carbon fuels elsewhere in the world to sort of be able to compete with our ability to create power. And so we might, counterintuitively, solving nuclear fusion at the moment might actually make the whole climate change problem worse.
Curious. It's interesting. You mentioned your robotic technology for assembly and everything. A lot of that, you mentioned it came from Culham. A lot of that's been developed as part of Jet, I think, as a spin-off.
Exactly. Yeah. I mean, we've got a good relationship with Culham. Our chief engineer or our CTO is the former chief engineer at the UK AAA running the fusion program. So I think he can speak for himself, and he said this publicly that I think he lost confidence in nuclear fusion, and he actually thinks that space-based solar power is a much more viable solution than fusion, certainly in the near term.
Okay, no, brilliant. Thanks. I'll skip a few of the ones which I think you might have covered because we're always conscious of time. We've got a lot of questions. One from Vince. Do the panels get hot? How they cool? So we know space vehicle kind of thermal management's a big issue. So how do you cope with that?
Yeah, I mean they do heat up. So the sort of part of the inefficiency of solar power, they do heat up. So thermal management will definitely be an issue. So we'll need to find ways of radiating that heat away. And indeed, as we know on the ground, as I said about Saudi Arabia, solar panels on the ground also heat up. And so they radiate heat into the air, and which otherwise might be reflected back through the albedo process.
Do you have any particular research in that thermal management, looking at novel approaches there?
The engine, yes. I mean, I know the engineering team have been spending a lot of time on thermal management because I know that's factored into the design of these panels. Where the steps on the helix I've been talking about. I don't know quite how novel that is. I'm not sure at the moment, but yeah.
Just curious because NASA did some interesting work back in the 60s about sort of spraying stuff between kind of different collectors to do that thermal management.
Yeah.
Okay. Rob Williams, what effect on radio astronomy?
So there has been some work done on that. I think it's because we're in a very monochromatic spectrum that we're using for the microwave, where everything we're only using a very narrow part of spectrum. Outside of that, we would expect the impact to be quite low, but obviously in that spectrum, then if you're looking through or looking at the transmitter on the line of transmission, then you will see some interference. But because we've got this very large phased array transmitter, the ability to steer the beam and focus the beam is really quite there's not much leakage of radiation just because from the beam forming process, so that you don't leak much outside of that. So you should be able to avoid too much interference.
Okay.
So don't build a radio telescope near where you're dumping your energy down, is what you're saying. Is that correct?
I think that would be something to take into account when siting the locator systems. I think that's right. I think, but what we're also doing is creating the potential for new radio telescopes in space that you could put away from any terrestrial interference.
Well, that brings up an issue that had been, if I was sitting in space with an enormous amount of electrical energy available, might think of building a factory up there rather than sending the energy down to the Earth and losing some of it on the way. How does this fit into ideas of actually manufacturing or creating things in space?
So we're looking at that as a secondary market at the moment. We're focusing on the Earth, but there are plans. There are companies now who are putting or planning to put data centers in space and AI centers in space, and manufacturing facilities. People like Space Forge, who sure many people are familiar with, who are looking to manufacture semiconductors in space. BioOrbit, who are looking to do pharmaceutical development in space, crystal growth, protein crystal structures in space. So I think that's something that we're going to see much more of. I think we're all familiar with Elon Musk's view of mankind becoming a multiplanetary species as the future. I think Jeff Bezos has quite a different view, as that some people might know, and that his view is that, okay, well, maybe man can live in other places, or humanity can live in other places, but we've evolved to live on the Earth, so the Earth will always be the best place for human to live and thrive. So let's zone it, residential, and put all the industry up into space and keep the Earth as pristine as we can. So his concept for space is that we actually do more of our infrastructure in space. That's where Kuiper comes from. He's moving creating a global communications infrastructure in space, which will then underpin data infrastructure and furtherly manufacturing and a whole range of other industries.
Okay. Let's pick up on a couple of questions. I noticed that Howard Bromley, I don't know if Howard wants to ask his own question. I can't see him on the array. Anyhow, Howard,
yeah, I can if you like.
Oh, go ahead, Howard.
Well, the first one was just about the susceptibility of our power source to Kessler cascade. And then the second one was, can the phased array be focused sufficiently to weaponize it?
Okay, so the first question is a bit of an echo coming through there. Is it? Okay.
I've muted.
So so the first, so I think when we're looking at the orbits to locate some of this infrastructure, that's definitely something to focus on. Certainly, low Earth orbit is becoming increasingly vulnerable to Kessler type events, and specifically in the very narrow geostationary band where all the communication satellites are and the weather satellites. They're similarly, there are risks there. So we'd be looking to avoid those. And as I think I said, particularly for the very large structures, we need to put them somewhere in orbit where they're a 24-hour period orbit, so that they cover the same part of the sky as where they're distributing power to. But they don't need to be in that very tight band where the geostationary satellites are. So we can use parts of space that are very currently underutilized in that sort of area. But in other orbits, particularly if you're passing through LEO space, it gets more tricky. So we'd have to be quite careful about that. And on the other point of can you steer the beam so that you could make it more used as a weapon? You could design it so that you could. Ours at the moment is specifically designed so that you can't. So the structure is designed, so that you have the right energy density on the ground to be compliant with energy regulations, and make it impossible to be hijacked, if you like, and used as a weapon. There are some of the people who are working on space-based solar power solutions are looking at laser-based energy transmission systems. So that in those situations, the energy is much more intense, is much more dense, and those are probably the solutions you'd be looking for if you were looking to create an energy weapon.
I think laser suffers from kind of degradation through the atmosphere, doesn't it? Which radio wave doesn't
It
really
does.
so much.
Exactly. That's yeah.